Hello, everybody. I'm sorry I'm late. There we go.
You're good, don't worry.
All right. So I rushed out because I had been working all morning on this NSF proposal. So I lost track of time. Then I ran out without my mask, so that didn't help. All right, this is actually the last topic that we need to discuss here under soil mechanics. And that is slope stability analysis. Okay, so those are the topics that we've covered. You should be familiar with most of those. We've been doing that in life, right? We did the soil gravimetry and the soil texture and soil consistency. That was the Atterberg limit. We're working on the engineering soil classification and compaction consolidation. I don't know why. It seems to me fluidization and liquefaction ought to be in that list too. I don't know why that isn't there. But anyway, so those are the topics we've covered today, and we just finished with subsidence, and this is our last topic, and that is slope stability analysis. And this is the way engineers approach the subject, is that they just break a hill slope up into a bunch of slices, and they treat those as if they are blocks on an inclined plane. And so essentially, they're doing exactly the same kinds of stuff, only now you have to sum all the forces that are either acting to drive the motion or acting to resist that motion down the slope. So here's another look at what we're doing for a soil. If you have a potential failure surface, say you're coring down along line H, right? So you're getting down in there. And what you want to do, of course, is figure out what the forces are and balance them. So the force of gravity is pulling that slice. You notice that with H as the sides, it's a parallelogram, isn't it?
Dr. Franzi?
What?
Are you screen sharing?
I'm sorry? Oh, you don't think okay, thank you. I thought I was, I guess I wasn't. Gotcha. Yeah, that was me. There we go. Okay. So, well, then let me go back to the beginning here and take a look at this. This was slide number 1. We're looking at the method of slices here for slope stability analysis. And we're breaking the slope here up into 7 main slices. And this was the second. So if we have a soil where we drill down to a potential failure surface and we know that distance is H, we can, the weight of that block, right, is just going to be the unit weight of the soil times the distance X, which is the distance perpendicular to the layer. And so to get that, all we have to do is multiply H times the cosine of theta. That gives us X. Our thickness, and remember, we always do this 1 unit into the board, right? So we take, for example, for our normal force, the 31.95 kilonewtons per, oh, I'm sorry, 21.7 kilonewtons per cubic meter gives us 31.995 kilonewtons per square meter. That's our total load. If we take that total load and multiply it by the cosine of 30 degrees, we're going to get our normal vector. And if we take that stress and multiply it by the sine of 30, we're going to get the shear component, the shear stress component. Right? So that's just different ways of looking basically at the same problem here. So it's what we've been talking about all semester, or at least this part of the semester. So now what we're going to do is take a look at if we're going to do this on a slope, we're going to have many, many slices. And back in the day, when I did this stuff, there were no real spreadsheets. There were no spreadsheets that I had access to. And we had to do this all by hand. So you'd probably do, 7 or 8 slices per hill slope as a demonstration sort of a thing. I guess I can make that a presentation. Yes, sir.
That best in this case is not factor of safety, right? Or is it
This is going to be the factor of safety, because what you're going to do, if you look at this equation, that is factor of safety. The cohesion times L, and L here is the length, the total length of the arc. Okay, that you're calculating what the resisting force is due to cohesion there, plus W cosine theta for each slice. That's what these numbers all amount to, right? I is sort of a counter. So this goes, we're going to sum all these normal stresses. We're going to do this operation for each slice until we reach n slices. Okay, that's just the summation notation. So we're going to take the normal stress, and by the way, that is the Moore-Coulomb equation, is it not? C plus sigma n tan phi. And so we're going to use the Moore-Coulomb equation to calculate the resisting stress, how much stress that particular slope can withstand before it fails. So the cohesion part is C times the sum of all the little L sub i's, right? So the distance from, I should do this on the screen so you guys can see the cursor. We could define little L sub I as the distance, kind of a straight line distance between the two sides along the base. That's the length of the failure plane for that particular slice. If we sum all of those up, we're going to get big L, which is the total length of the failure surface. And we're going to multiply that by cohesion to get the total amount of cohesive strength along that failure surface. Then I rearrange the equation a little bit for what you're used to. Tan phi times the normal stress, which is W sub I cosine sub I, minus the pore pressure. The pore pressure happens to be for that particular slice. And so that's the Moore-Coulomb, that's going to give you the shear strength. The shear force that's applied to this surface is going to be the sum of, again, this is for a circular slip, it's going to be the sum of WY sine length of the entire system. Okay. So let's go here. Yeah, so L was the entire curvilinear distance along the bottom of the failure. And in this case now, we're going to have 8 slices for the 24 meter. You notice here that we're along a circular failure surface. This is the Frobenius method. It's also called the simple method or ordinary method of slices. And so we assume that slide is going to rotate around some circle center up there in the air, in this case, and that it's going to cross these boundaries and emerge over here. So we would just, for example, for that circle that has a 24 meter radius, we're going to go through and calculate the factor of safety. And we have to make a lot of assumptions here. First, let me just say that for the Frobenius method, the side forces, now we all know that these aren't independent slices, right? We're assuming here that the resultant of all the side forces is 0. they balance. That's not going to be true, of course, but it's close enough generally. Yeah. Well, each slice is confined by other slices, right? So there's going to be shear forces in there, and sometimes those shear forces have a normal component to them. So you have to resolve all that stuff. But if you assume that the side forces cancel, they're going to be small differences for the most part. So if you assume the side forces cancel out, then you don't have to worry about them, and that's what we like. We like to make things simple. So now we have no idea. If we go ahead and we calculate a factor of safety, let's say it comes out 2.98. We have no idea whether or not this slope condition is going to fail along that circle, right? It could be along the one that's 21 meters for a radius. What we would like to do then is to do the greatest number of possible failure planes and then find the one with the lowest factor of safety, right? That would be the best way to do this, because you don't know, most times you don't know a priori which one's most likely to fail. I don't know. And so, and the other thing you want to do is, you only got 8 slices here, so the coarser or the wider your slices, and you'll notice they're not all the same width, right? They don't have to. They're all independent little things. You're going to sum them all together. But you only have 8 at the most for this, only 6 for the smaller radius one. And ideally, you'd like to have, the closer, the narrower the interval there, the more the true solution. You're kind of converging on the true solution. That's calculus, right? When you get the infinitesimally small distance between those slices, you're pretty close to what the correct answer would be in terms of the forces acting on that. So the way we can do this then, we're going to go through a couple of examples. Yeah, so the way we would do this is with a computer. There are programs, they're called limit equilibrium slope models. And they're called that because you're basically calculating some of the forces at the point where this thing's going to fail. You're going to get the smallest factor of safety by doing this approach. So with a computer, you would lay out, let me see if that, I'm pretty sure that's the next slide. Yeah, there we go. You would lay out a grid somewhere in the atmosphere, okay? Lay out that grid, and you would start kind of seeking what the true slope, what the factors of safety are for each node, each cross of that crossing point, intersection point on that grid. So you notice you may stop. Let's start right here at 1.55. So let's do 1.62. So it looks like that's where he's starting. So you would say, I want the circle to start here. I want, in this condition, for this situation, I'm looking at a bedrock surface underneath that earthen dam or embankment. And I'm thinking, boy, that's a really good surface to serve as a potential failure. All right, so I'm already making an assumption here. So I'm going to say, I want you to draw me a circle, right, with this as the circle center, and it's going to be tangent to this surface down here. Okay. And then, so you get 1.62. Then you tell the computer how to move around on this grid. You're going to say, I want you to go down vertically to the next intersection point down here at D1. And I want you to recalculate a circle so that it's also tangent to that surface. Well, this one came up to 1.85. So the program will say, okay, well, that's higher. So there's no need to go any farther in this direction. Let's go up, or let's go to the right. And so it goes to the right there, and it recalculates this again, tangent to that surface. And you get 1.66. Well, that's higher, so let's go over here. Let's go up one. Well, that's 1.62. That's not really very good either, is it? And so the program will keep drawing circles, kind of hunting around on this grid and assigning factors of safety to all of these grid nodes. And then what they've done here in the example is they've contoured that surface. So you can tell that somewhere in here is it's going to probably be less than 1.43 based on the way that it's been contoured here. And so that would be a likely circle center for all the circles that are tangent to that rock interface. And of course, that's the one that's the red line. So that looks like a pretty good solution to that. Now you can also tell it, come here and give me 10 circles spaced at 1 meter intervals. You have quite a bit of flexibility here. The program I used to use, it's not even in use anymore. It was called Staber. And with that program, you could break that embankment up into 200 separate slices. That was the default value. You could actually do more if you wanted to. 200 seems like a lot for something of that dimension, right? So, yeah, and so that's how we go around trying to balance this, the forces here, and figure out where the most likely plane of failure would be for something like this. And you notice that we also have the attic on here. So this is the water table, right? This is the water table, and I suppose you've got some kind of a drainage blanket here that is not shown on this particular example. But a lot of times what you do underneath these dams, if you want to lower the water table, is you put at the distal end what's called a drainage blanket. That's solid rock there. And, oops. This is really, really coarse gravel, some kind of something that is very, very permeable in here. So if this is my core, here's the tailwater, the backwater. There will be a huge drop in head through that impermeable core material. And then normally the water table would do something like this. But if you put this blanket here, that becomes the discharge point. That's so infinitely permeable compared to the rest of the dam's shell that the water table actually does this. So you've successfully then lowered the water pressure near the tailwater, and that's a good thing, right? The farther back you construct this, the steeper the hydraulic gradient, but again, you're dewatering the back end of it. Yes.
Would that kind of just like destroy the shell on the core by taking particles out of it, though?
You mean that they would wash into here?
Yes.
Not if you design. There are very specific requirements for drainage. So you don't just take a bunch of rocks and throw it in the trench and call that a drain. Basically, what you do is you design it with finer permeable material, and you get progressively coarser. And then you get progressively finer again. And the idea is that those fine layers prevent particles from washing in to the really coarse stuff that's in the interior of that drain. Okay, so all these things are very carefully designed by engineers so that they don't do that. But yeah, you could theoretically. We'll be looking at slides of the Teton Dam disaster, and that was a case where the dam failed because they didn't put much core material in there. In fact, when the Army Corps went in after the dam failed and cut through the dam to expose the side and see what the heck happened there. And it was very difficult to see that they used any really impermeable core material for the interior of that dam. And what happened was, if there's no core material, then you're really in trouble, because now you've got a high hydraulic gradient coming out, and you can get spring sapping or piping. Piping and spring sapping are two very analogous processes. Spring sapping is where natural groundwater comes out, and it removes some soil particles, and everything kind of collapses simultaneously into that area that was vacated. With piping, the structure is undermined by that erosion, and it actually creates a tunnel or a pipe in the subsurface. And so both kinds of failure can happen. They have very, very similar mechanisms for erosion. All right, but all of that goes into, so all of these things. So if you design, let's say you have a highway embankment, and you want to make sure that it's going to be really safe, you can practice with some different designs, right? You can say, well, what if I made this a 2-to-1 slope or 3-to-1 slope? Isn't that as much save you some money? Well, you do that, you find out your factor safety is poor, then you can lower it. So you get into that range of safety factors that you want. All right, so these slopes are then sort of engineered. Now, I don't know if you remember the talus slope that we saw in Iceland, where it had started to slide, and the Icelandic Department of Transportation had done some things to clear that slope. Well, what's going to happen there is that slide is going to continue to cut back until, again, it reaches that angle where the factors of safety are the forces driving motion and resisting motion balanced again. And that's all you're doing, is just balancing forces all this time. Okay, so we're going to run through a couple of examples here. And so it's, again, a nice, simple sort of solution. And in this one, we have a unit weight of 19.4 kilograms. That should be cubic meters, right? 19.4 cubic meter, kilograms per cubic meter. We have a internal friction angle of 23 and a cohesion of 0. Where do we get those values from? How would you get the values for phi and c?
Those would be from like some sort of shear test.
Yes, they would come from a shear test, right? And that is those are the coefficients of the Moore-Coulomb equation for the Moore failure envelope on a triaxial test. Okay. Good. So this turns out that it's really well suited for a spreadsheet analysis. That looks like a spreadsheet, doesn't it? All right. So go along the top of this thing. It says, here's our width. Well, how do we know our width? We're going to scale that right off our drawing, right? 1, 2, 3, 4, 5. So each one of these blocks is 4 meters square. And you notice that there's no vertical exaggeration in this, right? There's no vertical exaggeration. And so we can calculate the width. Now, for this first slice, this is really a triangle. The side here is 0 thickness, and at the other end over here, it's, well, let's see, 4, 8, about 12 meters high. Okay, so the average height would be 6, what's the area of the triangle? 1/2 the base times the height. So the base would be, well, let's see, maybe it cuts into this square a little bit. It starts in this square. So let's say it's about 8, 7, 8, something like that. You're doing this much more precisely. So that's your base, and your height is about 12. So 1/2 of that would be the area, and you have 1 meter into the drawing. Right? We're doing this per unit width. Okay, so I said that the width was 8. The height is 0 at the upstream end and 12 at the downstream end. The basal elevation is 60. That's for all these things that go 1 and 2. That's for the upstream, the upslope side and the downslope side. Yes. Right. So 60 and 48. Let's go back. That's the elevation of the red line. The upslope part and the downslope part. So you're at 60, and then you're at about 48. Okay. That's going to. Does that matter for calculation? It does, because that's going to give you your height. You want the average of that, don't you? You want the average of the difference. So you take that would be the 12, okay, which divided by 2 gives you 1/2 the height. Okay, so the next one on slice 2, just so we can prove that, we said that was 12. So this one is way down here. Instead of counting squares up, I'm going to say that that's about 23, and that's about 12. So that should be about 11. Right, the difference? Okay. So let's go here. Yeah, 20, well, that's close, isn't it? Oh, the downstream on the upper one was 48. These two will match, just like these two match. All right. So that first slice, then we can calculate the volume. 1/2 the base times the height. So it's going to be, if you take this as the base 8, take that, that's going to be 4. If you cut it in half, multiply it by the height, which is 12, right? And you get 48. So that's and 1 meter into the board is 48 cubic meters. The slope angle, well, all you need to do here, right? There can be a pretty steep slope here for the first leg, but you can just take the x and the y dimensions, so you can use some trig, right, to calculate what the slope angle is. That would be the adjacent side over the opposite side, so that you're going to use the tangent line to get that. And then you can calculate the length of that, the hypotenuse, the length of that slice. That's your actual failure surface. So let's go back. Oops, not that far. Go forward. So you'll notice here, there's my angle. So what did I do? Here's the basal area. That's my failure plane. I calculate that. Once I know what else the length is, I can use that for my basal area calculation. So the normal force is going to be W, right, of the first slice times the cosine theta. And we just calculated theta in degrees. It's 56.3 for that first slice. That's our slope. The shear force is W sine theta. And the water pressure is 0, because in this case, we're doing a dry condition, no water behind us at all. So we don't have to worry about water pressure, we don't have to worry about water forces here. The basal area is the length of that failure surface times 1 meter into the page. And so I can calculate the effective normal force and the shear strength from the Moore-Coulomb equation for that slice. So I've got the resisting and the normal forces for that particular slice. I do the same thing with slice number 2. Okay, so what is that? 4, 8, 12, 16, call it 18 meters wide. Yeah, you just put in all these dimensions into the model and calculate all of the forces. Then you sum them all up. And so I get the total shear force here, the total normal or resisting force from the Moore-Coulomb equation, and I get a factor of safety of 1.253. That's not real good, but you know, at least it's above 1. That's something to be happy about. Yeah, now you'll also notice that I have all these A's and B's in here. Right? That's for the next step. So we sum that all up and we get 1.253. Now I can put a water table in there. The first slice is still going to be dry. Now you know where the A's and the B's come in. Now I have to calculate, you notice that they have different unit weights. If you look over to the left, if it's dry, it's 19.4 kilograms. Again, that should be cubic meters. I probably just cut and pasted that because I hate doing superscripts. And didn't notice that I didn't do that correctly, but I'll fix that. And when it's saturated, it's 25.4 kilonewtons per cubic meter. So the sample weighs more, makes sense. And it's the same internal friction and cohesion coefficient here. And the same circle, right? We're still working on that same circle. Okay, so now we calculate our volumes. But we also have to calculate the volumes for part that's wet and part that's dry. Right, so we break it into some additional calculations here. We get our total normal, total shear. Now we have water pressure to contend with, except for slice 1. Right? That was still below the water table. And we have to subtract off to get the effective normal stress. We have to subtract off that normal, the water pressure term. And we end up dropping our factor of safety now to 1.027. So putting water in this thing has really severely decreased our factor of safety. Okay. Well, so now you can maybe start seeing the value of all of this. Okay, so if that had pushed us below, actually we probably want to fix that anyway because that's not very good number. Right? We could do that blanket thing if we wanted to. We could do a lot of different things. Sometimes what they do is they drill horizontal wells into the side of the embankment, and they serve as drainage points, kind of like the blanket idea, right? But you just drive this thing in sideways under the embankment, and it drains the water. Anything you can do to drain the water out of a slope is going to bring that factor of safety up. All right, good. So now what can we do? Well, let's play around here. What happens if we decide that we want to build a house here? We want to cut into the bank. All right, so we have our water table. It's in the same position as before. But now we've taken out slice 9. Well, if you recall, well, look at where. Oh, I didn't even point this out before. 7, slice 7. Slice 8, all of these forces are directed in the opposite direction, aren't they? And that's, here, I'm going to go back because I forgot to mention that. That was my bad. You notice down in here, the shear force, it's negative, isn't it? Right, because we do the sign convention where the positive value is the shear force is downslope, and we do the negative when it's pointing back up the slope. So we would actually, when we're summing up the shear force, we actually subtract these things. Good, yeah.
Wouldn't that just basically depend on where you put the center of the circle?
Absolutely, and there's an infinite number of possibilities, isn't there? So you have to put some kind of constraints on these models. You have to tell it. In this case, all we're doing is comparing what happens when we take one circle and change the stress conditions on the slope. But if you were truly looking for the minimum factor of safety, you'd want to do some kind of a search algorithm so that you could have the circles, you know. I know when I did the Waylandsburg landslide, for example, we had a bedrock surface, and I told the computer to do circles to 10 different horizontal levels, one of which was that bedrock surface at the bottom. And so I got 10 circles for every point. Some of them actually missed the slope entirely because they were so high up. Yeah, so in this case, we have to subtract off all of this. We actually use a negative theta as well, right? Because it's directed back into the slope. Okay, so when we remove slice 9, we basically take slice 9 out. I don't even have to change my table from the previous one, right? I just zero all that stuff out and sum them all back up again. And what happened? We lost that variable force that's holding the slope in place. If I had put back in that negative value here, it would have raised the factor of safety because it would have decreased the shear stress. Right? Think about what it's doing. This is the shear force. And so when I put a negative shear force on there, it actually increases or decreases the overall shear stress. Right? It's going to decrease the shear stress. Okay, so that's not good. That's very, very, very bad. Well, so I did that, and I said, well, okay, so I'm not going to cut into the bank. I'm going to put my house at the top of it. All right, so I put a layer of soil up there. I'm going to do some pre-consolidation, right? That's how we do that. Right? We load the soil and let it consolidate for a period of time so it packs down. So I put a negative amount there. What is it? So 4, 8, 10 foot layer of soil, so it will pack the soil down for me. All right, so now look at my slice 1 is much thicker. 2A goes all the way up to here. So I have to recalculate now the size of those guys, those ones. And here you go again. Yeah, that does. Now what I've done is I've increased the driving force at the top of the bank. So I've added more positive shear force to the top of that bank. So this just shows you how you can kind of play around in different scenarios. And these are all called limit equilibrium. This is the Fellenius method of slices. It's the simplest of the ones that you might encounter, and it's very amenable to a spreadsheet. I mean, you can put in 20, 30 slices, 40 slices, 50. You do as many as you want if you've got a big enough spreadsheet. Spreadsheets can hold a lot of information, and you can do these very quickly. The only thing you want to do is figure out some way to search for the minimum factor of safety if you're actually doing this. That's what these other limit equilibrium programs do. Okay. There are some other ways we can do this. What if we don't have a circular slip? Or no, I'm sorry. So we're still going to do a circular slip here. This is the Bishop's method. And so, but we're going to look at the forces now. Side forces are going to get factored in. Okay. So we're trying to account for some of these side forces here. Now, this one, you can't solve this exactly. You have to do it iteratively. So that means that you're going to take a value for this Bishop coefficient, try it with one, see what the solution is, then try it with another, and you're going to choose the one that has the least factor of safety. So it has to be kind of an iterative process for you to do that. right? Well, what if you don't have, I mean, that's assuming a circular slip as well, and that's just not as good. What if we have a non-circular slip? Like for instance, on that first one, we had a horizontal bedrock surface. Maybe that thing's gonna slide over the bedrock surface as a planar slide for a long time. So you can do this Morgenstern-Price solution, and it's all on how you account for the forces. But they're all based on the same thing. You just balance the forces for all of these different slices and add them all up to get your factor of safety. So that's a very, very, very quick introduction to slope stability analysis. And I notice I'm under 10 minutes here, so yeah, I'm under 8 minutes. Okay, and so for those of you who took geomorphology, this one should look pretty familiar to you. So, and hopefully it means a little bit more to you now too, right? When you look at this. So, mass movements on slopes, you can either increase the shear stress on the slope or decrease the shear strength on the slope. So removal of lateral support, that's like removing that slice 9 that we were talking about in the previous example. When you do that, you are removing lateral confinement, and that's going to decrease your factor of safety. That can be doing, that's what anthropogenic activity, that's kind of what we do when we undercut the toe of the slope. But that can happen naturally too, can't it? It can happen on the cut bank of a meander. In fact, that's what happened with Wayland's. That hill slope was undercut by the Roquette River and finally reached a critical condition and removed enough of the lateral support, 2.5 acres split into the Roquette Valley. Adding additional mass. Well, we just showed you, we piled a 10-foot layer of soil on the top of that bank, and that decreased the factor of safety because it increased the driving stress, right? It didn't, the soil wasn't affected. We didn't touch the soil here at all. All we did was load it differently. And so the soil still has its cohesion, still has its internal friction angle, it hasn't been altered. And so that's the addition of mass. And that, we can do that, humans do that all the time. Mine tailings, big catastrophes have happened when big piles of spoil left over from mining fail as a result of over-steepening. And natural causes could be the addition of mass from rainfall. Take a dry slope, you're actually doing two things here, aren't you? When you saturate a soil on a slope, you're increasing its weight, and that increases its driving force. But what else are you doing? You're increasing the pore pressure, you're decreasing the normal stress, the effective normal stress. So you're doing two things to it, and that affects its strength. So the addition of water to a slope does two bad things. That can converge towards a factor of safety less than 1. Earthquakes, now, we can't account for that with an equilibrium model like this because these are ground accelerations, right? These are the kinds of things that cause shaking, up and down. Up and down motion is, what are those waves called? For the surface waves in an earthquake. Those are called Rayleigh waves. And the ones that go side to side are love waves. So that slope then has got stress from the momentum of that shaking. So that's a little bit different, and we don't necessarily account for that. Regional tilting, that's just increasing the slope slowly over time, and so that makes sense, right? You're going to change the stress condition. Removal of underlying support, well, this is subsidence, isn't it? If you're taking stuff out, you're creating a difference in the stress distribution in the vertical. So solutioning, weathering, undercutting, mining, karst, you know. And then lateral pressure. This can be caused by swelling clays. If you shrink and swell and shrink and swell, you're putting some lateral force on the soil as well. So all of those are altering the stress condition. On the other side, weathering and other physicochemical reactions. So now let's take a road embankment or a road cut. A lot of the highways in New York were built in the 40s and 50s, mostly in the 50s after everybody came back from World War II. The Army Corps started building dams and started building interstate highway, the Eisenhower interstate highway system. And so when you cut rock, it's nice and fresh at first, but it's got fractures in it. And water's going to move through those fractures. And as it does, it's going to weather them. So primary minerals that were providing cohesion, that were providing internal friction, they're weathering. What do they weather to? Clays, right? You take a feldspar and you weather it, you end up with a clay as a residue. And so slowly over time, the internal friction and cohesion values slowly deteriorate and change. And that is you're reducing the shear strength by doing that. Shrink swell can cause ground fractures. That's another thing that can happen. Or solution widening of joints. Right? All of that stuff will decrease the shear strength. So pore pressure, we've already talked about that. That's going to decrease shear strength by decreasing the effective normal stress. Capillary tension, however, when you develop menisci in the unsaturated zone in pore spaces, that actually adds strength. Capillarity is actually negative water pressure. It's water that's held in the soil against the gravitational force that's tending to pull it down through the soil. All right, so that's a negative pressure, which means it actually increases the effective normal stress. That's why we can get over-consolidated clays in the vadosome, because it's alternately wetting and drying and wetting and drying, and that pulls those particles together and over-consolidates them. Remember what over-consolidation is? Good. That's a good thing. And then structural change. Yes, you got to change the structure of the soil, so that makes sense too. Okay, so we're going to talk about, it'll be very similar to what we did in geomorphology, look at some different kinds of mass wasting, and look at some case studies for engineering as well. All right, so that's enough for today. Yes, it is, because it's 11:49. Any questions? You guys in the online group, you're all set? Yes, sir.
So when you go back to the Bishop method,
Yep.
then you look more like viscous sediments that you maybe see that?
No, all you're trying to do is account for all of the forces that are operating on the slices. Felenius is just a quick method to get a good approximate answer. And it's very adaptable. There's a lot more calculations. I mean, now in the day of high-speed computers, it doesn't really matter. You could do Bishop method and account for those side forces. Felenius just ignores the side forces.
Okay.
That's the big difference between them.
You said that it kind of like slides along the plane on the bottom, right?
Oh, no, that's the Morgenstern Price. That's the non-circular slip.
Okay.
Yeah, and so if you have good subsurface information and you know that there's a stratigraphy there, right? Then you say, well, I'm not going to use a circular slip because, you know, so you got this and then this. You might find that your slip does something like this. Right?
Oh.
So that will account for heterogeneity, right? Remember heterogeneity? That'd be a good thing to remember too. Oh God, yeah. Yeah. Nobody does this by hand anyway. Yeah.
So we're not going to go by hands to this class.
Well, you'll notice that I'm kind of struggling right now to stay on top of things because I've got that mapping project that starts today. And I also am on this NSF grant that the deadline for that is the 13th. So I'm a little under the gun here myself. So I probably won't make you do any slope models, or maybe we'll do it as a demonstration in lab. All right. I mean, it would be good for you to walk through it. In fact, what we can do, now that I mention it, is we can go back to, I still have the spreadsheets for this, and we can change the position of the water table and have you run a scenario. It's a very simple thing to do. So maybe we will do something like that, maybe not as a homework assignment, but as an exercise in lab. Because I do think it's important for you to get that information. Are we good? Okay.
Bye.
Bye, guys.